So in the previous class, we have gone through uh, the basics of like how the electrons and holes are generated, and what is the role of electrons and holes, and how the mobility is defined, and in what manners the drift velocity is going to affect the current flow. We have seen all that, and how the drift velocity basically generated in the presence of electric field. We have gone through that. So with respect to that, we have find out like the current. So what is the current basically that we have obtained? Like a current is basically generated when the electrons are basically flowing, and that electron flow is at you can say equilibrium. Once uh, the thermal equilibrium have been obtained, the electrons is basically having constant velocity, that is called a drift velocity under the effect of electric field. With respect to that, it will be constituting a current. So now the next point we will be seeing is the current density. So here, so once we are having a conductor, we will basically see like how we can uh, define the current density in a semiconductor or any conductor. Okay, so here uh, suppose this is the conductor, and it is having a length L, and this is its cross sectional area. And suppose this conductor is having n number of electrons available in this conductor. Okay, so here this n is basically the number of electrons contained in this L length of the conductor. So here like n is the number of electrons inside the L length of semiconductor. Okay, and suppose t is the time taken by an electron from traveling from one end to the other end of the conductor. So here we are considering like t is the time taken by an electron to travel L length of the conductor. Okay, so if these two points we have seen, then the total number of electrons that are passing through this cross-sectional area per unit time, if we need to find out. So total number of electrons are n, and it is taking one electron is taking time, that is t, to cross from one end to another end. Okay, so at a particular time, what number of electrons will be crossing this particular cross sectional area will be given by the total number of electrons that are available divided by the time taken by one electron. Okay, so that much of time taken by one electron, so total number of electrons that will be passing through this cross sectional area will be this. Okay, so here it is total number of electrons passing through a area. Okay, so these are the total number of electrons passing through this. Okay, but if we need to find out the current, so current is rate of change of charge. Okay, so these are electrons. So if we want to convert this electron into charge, so we will be multiplying the number of electrons with the charge, well, charge of one electron, that is q. Okay, so if we need to find out the total charge per second passing through the particular area, that is, this is what total electrons passing through a particular area, this is total charge passing through area, that is basically cross sectional area A, that will be n will be multiplied by q divided by t. Okay, so just we need to convert this electron into the charge. Okay, so n into q will be charge per unit time. So this charge per unit time is nothing but your current. Okay, so that means this current passing through a particular conductor will be defined with respect to this. Okay, so here
हेलो सर सर
time that,
हेलो
yes,
सर बहुत ज़्यादा ग्लिच आ रहा है लाइक
yes,
आप जो बोल रहे हो और जो स्क्रीन पे आ रहा है उसमें बहुत ज़्यादा डिफरेंस आ रहा है टाइम का अभी अभी वो एन इंटू क्यू बाई टी आ रहा है अभी
okay, okay, just a minute. Okay, so just go through this 2 to 3 minutes. Just let it be like it's a network problem basically. So with respect to that, now it may have gone. So this time that we have defined in current equation, the time can further be defined like time is velocity. If we need to find out the time, that whatever length is there in a conductor we have taken, this is the length, and each electron is traveling with a velocity, that is drift velocity. Okay, so electron is traveling with a velocity, that is drift velocity. So here we have the value of velocity and the length. So from there we can find out the time. So the time expression can be like the length divided by velocity. Okay, so by including the time in this equation, we can find the current. The current will be given like n into q divided by L by V. So here current can be given like n into q V divided by L. Okay, so this is current, and we need to find out the current density basically. So once we know the current density will be the current per unit area. Okay, so current density is current per unit area. So basically why we are finding out these terms, because these terms will be used frequently in the further classes, so that basic understanding should be there. Okay, so current density will be your current per unit area. So this current density is basically represented by a term called J. So J represents the current density. So J will be equals to NQV divided by L divided by A. Okay, so this will be your current density. So here the term L and A, L into A basically is the volume. Okay, so it is the volume. So we can uh, have the volume uh, term, and also if we combine the term like QV separately, and N L into A. So this gives us, this term gives us the electron per unit volume. Okay, so this is electron per unit volume. So as this is electron per unit volume, so number of electrons means number of free charge carriers per unit volume. So this is nothing but the concentration of charge carrier. So that is concentration of electrons. We can see concentration of electron. So this can be equivalent to N, that is the concentration of free electrons. Okay, so we can just write J will be equals to, this term is N, so N Q V. So here the current density we can define as the relation with number of charge carriers, number of free charge carriers, that is electrons basically, N multiplied by Q and the drift velocity. Okay, so further we know this drift velocity is, we have defined previously, mu into electric field. So we can write here, so N Q mu and electric field, that is E. So this is another formula to represent the current density, and the term, this term is basically considered as sigma. So your sigma is your conductivity. So if we want to write it here, so here this J we can further write sigma into E. So this relation is nothing but it is called the Ohm's law in terms of the charge uh, current conduction with respect to the charge density, current density and electric field. This is the relation also called as your uh, Ohm's law. And here sigma, that is sigma. So this sigma is called conductivity. Okay. So this sigma is given by N Q mu. Okay. So this is your sigma. This is conductivity basically. So here this conductivity expression also we need to remember. Sometimes in objective questions, the relation of conductivity with different parameters, like how it is on what parameters it depends, and based on that some objective type questions can be asked. Okay, so you need to take care of these relations. And in terms of the unit, if we want to find out the unit, like what is the unit of current density, so as we know the current density is current per unit area, so the unit will be ampere per meter square. So this is the current density unit. And in terms of sigma, if we want to have uh, the unit of sigma, just uh, by putting all this with respect to that ampere also we can define. So the unit of conductivity will be 1 by ohm meter. Okay. So sometimes based on this units also the objective questions can be asked. Okay. So here one more term we will be going with. So as the number of electrons or the charge carriers are there, once it is thermally excited, it acquires energy as it accelerated and its velocity increases, so it collided with each other. So collision between the charge carriers, that is electrons, is basically takes place as we have applied the thermal energy to the system, okay, to the crystal. So as the collision is going to take place, the power dissipation takes place inside that crystal. So power is dissipated in terms of dissipated uh, in term in terms of collision, or we can call it because of the collision. The power is dissipated inside the crystal, and that crystal will be like a metal crystal is there due to collision of electrons, we can call it. So that power is there. So if we need to find out power density per unit, that is power per unit area basically. So this power density is basically power per unit volume. So this power density is basically given by represented by the unit. Uh, this power density is also called as so it is power density to the power, that is watt per unit volume, that is meter square, and it is represented by the value, that is current density multiplied by the electric field, okay. Or in terms of conductivity, if we write this conductivity, it will be sigma electric field square. So this is the formula to equate the power density inside a crystal or inside a metal. So these are the basic terms that are most frequently being used in this device physics. So the next points we will be seeing is what is the electron and hole concentration in intrinsic semiconductor. So before going with the uh, doped semiconductor, that is extrinsic semiconductors, we will be proceeding with like the electron and holes. What is the role of electron and holes inside a extrinsic semiconductor and also inside a intrinsic semiconductor? So here we have seen like the conductivity is basically, that is sigma. This conductivity has the relation with the number of free electrons. So in that we have seen like the sigma is equals to n q mu, okay. So here this is the number of free electrons, or we can call it the concentration of free charge carriers, okay. So that like sigma is directly proportional to n, okay. So if it is a metal, the sigma will be high because the conductivity will be high. That means sigma is high means the number of charge carriers are high in that metal, okay. If we talk about the insulator, the number of charge carriers will be less compared to very less compared to the metal, because the conductivity is zero, almost zero in insulators, okay. So this n value is going to find out going to depict the value of sigma, that is conductivity of particular material. So n value is around 10 to the power 28 in case of metals, and it is around 10 to the power 7 in insulators. So in terms of semiconductors, we can see the n value will lying between 10 power 7 to 10 power 8. So this n in semiconductor we can uh, write like 10 to the power 28 to 10 to the power 7. It will be lying between this. So here basically this n that is here is this n is basically the valence electron inside the outer you can say valence electron or outermost cell is having whatever number of electrons in semiconductor, that will be your nscr. So as in semiconductors, if it is at 0 degree Kelvin, so if a semiconductor is there that is 0 degrees Kelvin, then it is having valence electrons, but that valence electrons are not free to move. Okay, so here why these are not free to move? Because in uh, semiconductors, if it is at uh, 0 degree Kelvin, basically suppose it is a germanium, so it is at 0 degree Kelvin. Okay. So here a germanium is there, it will be having 4 because it is a tetravalent. Okay, so all semiconductor materials are tetravalent. It is having 4 valence electrons in the outer shell. Okay, so this 4 electrons will be such that it is a crystal in the different atoms of germanium are there, and these are related somewhat like one germanium atom, another germanium atom is forming a bond by sharing its electrons or by sharing its outer shell or valence electrons basically. Okay, so 4 valence electrons are there, so it will be shared with one germanium atom will be sharing 4 different atoms and sharing electrons with 4 different atoms basically. Okay, so these interrelation between atoms by sharing the electrons is called a covalent bond. Okay, so basically the binding force, so here we can write like, so initially at 0 Kelvin, these free electrons, or we can call it the valence electrons that are available in tetravalent elements, are shared by the other 4 neighboring atoms. That's why these electrons are not free to move. Okay, so at 0 degree Kelvin, because of this covalent bond, because of this covalent bond, the semiconductor materials are basically not having any free electrons, so there will be no conduction. So this covalent bond is defined as a binding force, defined as the binding force between the neighboring uh, atoms, neighboring atoms, that is resulted from this binding force between the neighboring atom uh, resulted from sharing of electrons. Okay, or we can call it sharing of valence electrons. So this covalent bond is basically the bond formed between the neighboring atoms of tetravalent element by sharing its valence electrons. Okay, so by sharing whatever bond will be there, it will be a valence bond here. Okay, so here the shared valence electrons are basically tightly bound with the nucleus. So this is the nucleus. So these electrons are in close relation with or tightly bound with the nucleus. Okay, and also it is shared with the other neighboring atom. So it is not free to move. Okay, so that's why in semiconductor at 0 Kelvin is considered as an insulator. So here semiconductors at 0 Kelvin is equivalent to insulators. Okay, but if we are going to increase the temperature, okay, if we are going to increase the temperature, it will be like here. If we are going to increase the temperature, uh, what happens? The if we are going to increase the temperature that we are providing externally, that will basically uh, give it some energy to this bound electrons, or the electrons that are bonded with covalent bond with the neighboring atoms will be acquiring some energy. After acquiring some energy, it will be breaking the bond with the other neighboring atom. Okay, so that covalent bond is going to break basically, whereas we are going to apply the temperature. Okay, so by breaking the bond, the electrons will move from the covalent bond to become a free electron. And as the electron is moving from this location to become a free electron, it will create a space. So this empty space is considered as a hole. Okay, so this is basically the concept when if we are applying the temperature. So at 300 degree Kelvin, we call it room temperature. Basically, electrons are acquiring thermal energy. So these thermal energy that is acquired by the electrons are basically going to break the covalent bond. Okay, so once we have it has break the covalent bond, electrons will become free. Okay, so now electron have become free. So once the electron have become free, it will be able to conduct. Okay, so what is that sufficient energy that need to be uh, provided by in terms of thermal energy, so that the electron will break its bond in this covalent bond? So that energy will be equivalent to, so the energy will be equivalent to the band gap energy. Okay, so whatever, suppose it is germanium, so in case of germanium the band gap energy should be like 0.72 electron volt. Okay, so if we are providing 0.72 electron volt of energy in terms of thermal energy, then the um, this covalent bond will break. In case of silicon, we need to provide some more energy, that like 1.1 electron volt, as the band gap energy of silicon is higher, okay, than the germanium. So if we are able to provide Eg equivalent that is Eg equivalent amount of energy externally, then the covalent bond will break and free electrons will be generated. Okay, so here some points may be noted, like in terms of these are basically the electrons. So electrons have been generated. So what about the holes? Is holes is equivalent to electron, or how the holes are uh, related? So we will see. So basically the holes may also serve as the carrier of electricity. Okay, whatever comparable nature of the electrons are there. So if electrons are able to participate in current conduction, the holes can also be considered as the uh, carrier to electricity. That is, it can also participate in current flow. So the same effect takes place on the holes also. So if electron is able to move, and with respect to that, it is going to constitute the current, the hole movement will also be constituting the similar effect, and it will be once it is free, it will be constituting the current. Okay, so we will see how the holes are going to affect the current flow basically. So here hole, okay, sorry for the disturbance. Okay, so here we are going to see the effect of holes. So once we are going to provide thermal energy, so what happens once we are going to provide the thermal energy, the holes are being generated. So holes are having the same effect as the electrons. So here we may say like the carrier uh, capabilities of holes are equivalent to the electrons. Like uh, holes are similar to like electrons, but it is having the opposite charge. Like electrons are negatively charged, the holes are considered to be positively charged. Okay, and also once it is considered to be a positively charged, this is like an assumption. It is not like electrons are negatively charged, but holes are considered to be a positively charged because these holes are reacting opposite to the electrons. So like electrons are moving, suppose uh, this is here, suppose this is electron. Okay, and if electron is moving from here to suppose a location this one, so here it will be creating a hole, and this electron moves to suppose here, so it will be creating this. Okay, so by putting an extra empty space, so the movement of holes are considered to be opposite to that electrons. So here we can say the movement of holes are opposite to the electron. Okay, so if uh, yes, okay, so holes are considered equivalent positively charged, and also its movement is opposite to the electrons. Okay, but in intrinsic semiconductor, because whatever intrinsic semiconductor is there, that is electrically neutral. Okay, so electrically neutral means the whatever number of electrons are available, the similar number of holes will also be available. That means if n is the number of electrons and p is the number of holes, then in an intrinsic semiconductor, if the semiconductor is intrinsic, it is electrically neutral, so the number of holes or number of electrons will be equal, and this is basically equals to the term called Ni. Okay, so what is this Ni stands for? This is called Ni means I stands for intrinsic, like N for concentration, so it is considered as intrinsic concentration. Okay, so N, that is number of electrons, will be equals to number of holes, that will be equals to the intrinsic concentration of the carrier. Okay, Ni in case of intrinsic semiconductor. Okay, so next we will see like what is the effect of a doping, and how we can convert an intrinsic semiconductor to the extrinsic semiconductor. Okay, so basically doping, so we will see. So basically we will see doping. So in terms of doping, we see initially we have intrinsic semiconductor. Okay, so in that intrinsic semiconductor we are going to add some impurity, that is called doping, or adding So doping is nothing but adding some impurity to the material. Okay, so that is either whatever type of material is there. If we are going to dope, that will be by adding some extra atom that is none that is other than the whatever material is, that is basically. Okay, suppose it is germanium. So if a crystal is of germanium, we are going to add an atom other than germanium. Okay, so that will be considered as adding impurity. Okay, so whatever element, suppose we are going to add phosphorus, so this phosphorus will be an impurity added to the germanium. So this method of adding impurity to the germanium is called doping. Okay, so by considering this doping can be done by two different type of impurities. Okay, so suppose we are having one type of impurity that is called trivalent, and another type of impurity that can be is like pentavalent. Okay, so if this doping impurity is trivalent, then a p-type extrinsic semiconductor will be formed. Okay, and if the pentavalent type of doping we are using, then it will be forming a n type of semiconductor. Okay, and both of these semiconductors, like p type and n type, now it will be called as extrinsic semiconductor, or extrinsic semiconductor, or we also call as a doped semiconductor, or we can call it as impure semiconductor. Okay, so as we have added the impurities, that's why it has become an impure semiconductor. Okay, so this is how the doping takes place. But in case of doping, if it is trivalent and pentavalent, so trivalent dopants, so the elements that we will be adding to have a trivalent type of doping, that doping elements are called acceptor ions or acceptor type of impurities. And if it is pentavalent, we will be calling it as a donor type of impurity. Okay, so donor type of impurities means it will be able to give an extra uh, electron. Okay, so first of all, this pentavalent is called donor, and this trivalent is called acceptor. Okay, so we will start with the pentavalent type of doping, or we can call it donor impurities. So this donor impurities are like this is the figure. So one of the donor impurity is SB, that is called antimony. Okay, so here it is of pentavalent. So it is of pentavalent means its valence electron or the outermost cell will be having 5 electrons. Okay, so if it is donor impurity, it is called impurity that is having 5 valence electron. That have 5 valence electron in its outer cell. Okay, so if it is having 5 valence electron, so this valence electron that are available will be, so here different germanium atoms are attached in a crystal. So one atom of germanium will be replaced by the impurity atom, that is donor atom. So this impurity is Sp, that is antimony. So it is having five valence electrons. So 4 of the 5 will be used for making the covalent bond to the 4 neighboring atoms of germanium, but one of the valence electron out of the 5, 4 will be used to make this covalent bond. The fifth one will be a free electron. Okay, that means once we have done the doping, there is no need to increase the temperature so that a free electron will be generated. But as we have done the doping, after doing the doping itself at 0 degree Kelvin also, we are having a free electron. Okay, so we have a free electron. So basically, uh, whatever a free electron is there, so this is called the fifth electron. Okay, so here the energy is basically required to detach the valence electron in case of uh, in order to basically uh, move this free electron to some higher energy level. Okay, so this is the fifth electron. So if we are requiring to move this fifth electron as it is free, but even if it is free, it will be requiring some amount of energy. Okay, that means we need to supply an external energy. So that external energy in terms of this pentavalent doped semiconductor will be very less compared to, like, previously we were requiring Eg amount of energy to move the electron from the covalent bond and move to the higher to make the electron free, and that can conduct to by moving the conduction band. Okay, so if we want to move the free electron to the conduction band, then we will be requiring very less energy once we have done the doping. Okay, so in terms of doping, now if we want to move this electron, so that energy that will be required, uh, energy required for fifth electron. So this fifth electron will be moving, and for that the energy that will be requiring is around 0.01 electron volt if it is of germanium. If it is in silicon, it will be requiring 0.05 electron volt of energy. Okay, so this is how the impurity has increased the conductivity. Okay, by providing an extra free electron. Okay, so if we are going to uh, add pentavalent type of doping, after this doping, whatever the type of semiconductor will be formed, that will be considered as of n-type semiconductor. Why it is n-type? Because it will be having uh, extra electron to participate in the conduction. Okay, or in n-type semiconductor, we will be having electrons, large number of electrons, as a large number of dopant will be added, so large number of electrons will be generated, so this higher number of electrons will be there, so these are called majority carriers. Okay, and holes in the n-type semiconductor will be less, so this electron will increase because of doping, but holes will decrease. So if germanium semiconductor was there, that if it was intrinsic semiconductor, at that time whatever hole concentration will be there, that hole concentration will further decrease if we are going to do the doping. So here this hole concentration will be decreasing because as we are going to make the doping, the whatever extra electrons are there, that will be occupying the hole that will be generated because of the breaking of the bond. So whenever the breaking of the bonds is going to take place, the recombination rate will become faster as the extra electrons are available as the fifth electron in the pentavalent type of impurities. Okay, so the whole concentration will basically reduce if we are doing the doping, but electron concentration will be increasing. That's why it is called majority carrier. Okay, and in n-type semiconductor, the holes are of less quantity, that is its concentration is less, so it is called minority carrier. That means the current conduction will be basically contributed by the electrons only in case of n-type semiconductor, because it is having larger quantity of electron. But in case of n-type semiconductor, holes are in less quantity, so it will be constituting very less to the current conduction. That's why it's called minority carrier. Okay, so and how like we have seen, like here we need to provide that much of energy to make the conduction. So how this comes? So basically, if we have done the doping, so the doping basically allows to form an extra energy level. Okay, so we are doing a doping. So once we have done the doping, in case of pentavalent, so pentavalent have done the doping, in that there will be an extra energy level will be created just below the conduction band, because our motive is to move the electron from valence band to the conduction band. Okay, but by doing the doping, donor doping, we are able to have a donor energy level just below the conduction band, and the gap between these two bands, conduction band and donor energy level, is 0.01. That is the amount that we were requiring for to supply the external energy so that the electron can move. Okay, so this was the case in germanium, and 0.05 is for silicon. If it is germanium, it will be 0.01 electron volt. If it is silicon, it is 0.05 electron volt. So the gap between donor energy level and the conduction band. Okay, so this will basically going to improve the conductivity by creating an extra a donor energy level just below the conduction band in case of pentavalent type of doping. Okay, so we can write the point like, uh, once we are going to add the donor atoms, suppose we have uh, doped with donor atom. Once we have done the doped with donor atom to the intrinsic semiconductor, what it does is basically it forms an allowable energy level. It forms allowable energy level near or just below, we can write level just below the conduction band. It will be forming energy level that is called donor energy level just below the conduction band. This is called donor energy level. Okay, and also this uh, donor energy level is because of the extra this electron, or because of the impurity that we have added. So energy level is basically formed by discrete energy levels of different atoms. So as we are going to dope this germanium with antimony, we are having large number of antimony, and these antimony are placed like discretely, or it is having a far apart. It is placed. Suppose another sp atom will be here. Okay, that will be forming a covalent bond with four different germanium atom. So the distance between the sp atoms are far apart. So this sp atoms are having far apart, so the donor energy level that is it is forming will be of discrete in nature. So this donor energy level So this donor energy level will be of discrete in nature. That means the energy level that is formed here, so this energy level will be discrete as the donor atoms are placed far apart. Okay, so donor atoms are placed far apart, and that donor atoms are basically going to constitute the donor energy level. And this donor energy level is not a, you can say, combined energy level. It is of discrete in nature. That means it is having different smaller energy levels, different energy levels with very less difference. Overall, by forming all these, will be forming this donor energy level. So in the previous classes, we have seen like how the energy bands are basically formed. So similar, like these atoms will constitute different discrete energies level that are very closely placed. So that will combinedly considered as the donor energy level. Okay, so this donor energy level will provide electrons that will be just closer to the conduction band. So once we are able to provide this much of energy, the electrons will be passing from this donor energy level to the conduction band. Okay, so this is how the current conduction takes place in case of donor type of impurity have been added then. So now the next is we are going to add acceptor type of impurity. So here we are going to add the acceptor type of impurity. The similar, just opposite to that will be there. So in acceptor type of impurities, basically here the dopant will be having a 3 valence electron, or it is trivalent. Okay, trivalent dopants or 3 valence electrons will be there. Okay, so one more point just we need to include. So there are some uh, donor atoms or impurities, we can call it. So there are some example of donor impurities, so that we should be knowing. So donor impurities are also, we can call it, n-type impurities. So donor impurities are the first we have seen antimony, it is Sp represented by a symbol, and phosphorus. Phosphorus is also a pentavalent dopant. Arsenic is also a pentavalent dopant, and bismuth. So these are the different pentavalent dopant. So in terms of acceptor, acceptor means uh, it is going to accept electrons. That means it will be creating holes to the crystal as it is going to have the doping. So in case of donor type of impurities, it is named as donor because it donates extra electrons. Okay, but in case of acceptor type of impurities, once the impurities are added to the semiconductor, it will be creating a hole. So as it is going to create a hole, that means that hole will be ready to accept the electron. Okay, that's why it is called acceptor type of impurity. Okay, so here the example of acceptor dopant are acceptor. So example of acceptor type of dopants, we can write like boron is one of the acceptor type of dopant. Then gallium, indium, and aluminium. So there are the different uh, acceptor type of dopant. So in case of acceptor type of dopant, we can simply say like here also it is going to introduce the impurity such that suppose this is the figure. So this is germanium, and we are having uh, indium as the dopant. So here it is having only valence electrons are 3. So it is tetravalent, so it will be having 3 valence electron. So one is an empty, like the pairing, that covalent bond that will be forming will be such that the 3 covalent bonds will be formed, but one will be uh, empty. That means it will be having a hole there. Okay, that means there will be no electron. So if there is no electron, that means there will be a hole, that is an empty space. So empty space is represented by hole. So this hole will be paired with the fourth germanium atom, but it will be such that it will be ready to accept the electron. So it will be creating a space just below the valence band. Sorry, just above the valence band. So just we can see. So in uh, this type of doping here, it will be forming an acceptor type of energy level. Okay, so here acceptor type of energy level is being formed just above the valence band. So here just above the valence band, and its gap will be similar to the gap that was in conduction and the donor energy level gap. Okay, so 0.01. So it will be just above the valence band. So here this will be
Sir,
having, yes.
sir, it's already 10:05,
Okay,
sir.
okay, okay, okay. Just I'm wrapping up. So this is just opposite to the donor type of impurities. So similar to the donor type, the impurities in case of acceptor will be creating a holes, and that will be forming extrinsic semiconductor, relatively called as p-type semiconductor. So here in this type of impurities, p-type of semiconductors, basically the whole concentration will increase and electron concentration will decrease. So this whole concentration will be higher. That's why it is called majority carriers, and this will be called as minority carriers. Okay, so this is all about today's class. We will see the next point into the next class. Okay, and if any one of you is having any doubt, you can ask, or we will be closing the class. Okay.